So as a beginner, when we start doing the solution of any through any FEA solver, the first question comes in mind is whether it is whatever the stress we are calculating through using FEA, it is giving us the engineering stress or true stress. By the way, the engineering stress is nothing but the force divided by the original area, while the true stress is nothing but the force divided by the instantaneous area. As if this bar is going through elongation, its area is going to reduce due to Poisson's ratio effect, and that is why, like, whenever any component is in tension, its true stress is always going to be greater than its engineering stress. So this boundary conditions of this is very simple. It is a bar with 1 mm square cross section, and it is constrained in this location and in this location, and we are going to apply a force in positive y with 121,000 newtons. So, by the way, to solve this, there are two methods. Firstly, first solution, we are going to use the linear static solution with which uses the small displacement theory. By the way, the small displacement theory is like the displacement is the linear function of, sorry, the strain is the linear function of displacement. The stiffness isn't going to change. We assume like the stiffness is 0% of load and the stiffness at 100% of load is same. And the third is like whatever the solution we are going to get is we assume like uh, the the geometry changes due to the application of load are very negligible. So it is almost zero. There will be almost no geometry changes taken into the account of the stress calculation. So we are going to review this. So if we see this, this has solved in Abaqus, and we can see this like 1 mm is the 1 mm sides of this bar is no longer 1 mm after the application of load. It is 0.98 mm due to Poisson's ratio effect, but the stress is like 12098.6, which is near to whatever we will calculate through hand calculation of the applied load divided by the original area, which is the initial area of this component, and it is coming out to be same. While this is with the linear static analysis. One other way to solve this is by using the nonlinear static analysis, where we can use the NL or in other solvers it is called as large displacement geometry, large displacement on, which assumes like there is a large displacement theory, which assumes like the strain is the quadratic function of displacement, and stiffness at 0% of load can change after you apply the loading. That means the stiffness of this bar can change at 50% of load or anyway in between. And the geometry changes are also included in the solution. That means the stress will also be this while calculating the stress, the solver will take care of the geometry changes. So uh, the right side is with the nonlinear geometry solution, and we can see like the change in the other dimension other than length are almost same as per the linear, whatever we have solved with linear solution, but the same node is now annotating the different stress, and it is larger than whatever we have calculated through the hand calculation or the linear static guide, which both are nearly same. So it is larger than that, and the bar is in elongation. That means whatever it is showing, it is the true stress. So whenever we want the to calculate the true stress, we can use the nonlinear static, and in most cases we are using that, the nonlinear static. But that doesn't mean we shouldn't use the linear static. That doesn't mean we shouldn't use the linear static solution FEA, because for some of the engineering problems we know that before even applying the load, the deformation is going to be small and the geometry changes will be negligible. And so whatever the engineering stress which you will calculate through linear static will be almost near to the true stress, so we can easily take the judgment on the basis of linear static. And by the way, linear static is quite easy to converge if compared to non-linear static. So for few of the problems, we can even use the linear static when we know that the deformation isn't going to be much. So that is a quick comparison of the stresses what your linear static and non-linear static is going to throw with a small displacement and large displacement solution. By the way, this problem has been solved in Abaqus. You can download the INP file from the attachment and you can solve on your own. And even though this has been demonstrated in Abacus, this is also true for other solvers like OptiStruct and Nastran or any other solver. The core basic FEA is same. So yeah, thank you. Have a great day. Bye.